We're taking you on a journey to revolutionize ammonia production. Our research adopts a photoelectrochemistry principle, offering a renewable energy solution. I'm ESMA.
And I'm ZIMA.
We are from Karisma Bansa. Get ready for a green future. Welcome to creating green ammonia from nitrate waste using photoelectrocatalysis system with modified TNT electrodes.
If we have your attention, fasten your seatbelt.
World Bank reported world population has reached 8 billion by 2023 and will keep on increasing. This leads to a higher demand of food and fertilizers. According to Statista.com, ammonia production, most widely used fertilizers, reached 150 million metric tons in 2022. Currently, ammonia is produced using Haber Bosch method, which requires burning fossil fuels with extreme conditions of 450 degrees Celsius and 28 ATM. As a result, outrageous carbon dioxide is emitted a lot, which contributes a lot to global warming. On the other hand, the rising rate of nitrate pollutants in the groundwater is worrying. It can cause colon cancer and blood disease, according to Shire 2019. Thus, one alternative way to solve these problems are by using electrochemical conversion of nitrate to ammonia.
Titanium dioxide nanotube, or TNT, is a highly affordable catalyst with a high surface area, great chemical stability, and to enable oxidant vacancy. Incorporating cobalt and electroreduction to TNT has been reported to improve electrocatalyst effectivity for aqueous nitrate reduction to ammonia. TNT itself is a renowned photocatalyst, which converts light to electrical energy. Inspired by natural photosynthesis, we study cobalt doping and electroreduction modifiers on TNT to develop photoelectrochemical system of green ammonia production, which are operable at room conditions using only pure solar energy input.
Our experimental setup consists of these steps. First, TNT synthesis by anodization technique, then TNT modification with cobalt doping and electroreduction to obtain 4 types of electrodes: TNT, co-TNT, RTNT, and RCO-TNT. Next, material characterization including optical properties using spectrometry, morphology character by SEM, and structural character by XRD. After that, performance evaluation of each electrode as photoanode and dark cathode. Afterwards, the evaluation of photoelectrocatalysis system to perform nitrate reduction to ammonia. Finally, ammonia measurement using UV-based spectrophotometry.
The synthesis of TNT was done by anodization technique in ethylene glycol containing water and fluoride electrolyte at 50-volt constant voltage for 60 minutes. The current generated versus time is recurrent and displays as an anodization curve, showing the 3 changes in the current profile. From the SEM top view image, we can see that the nanotubes are successfully formed with about 45 nanometers of inner tube diameters. This tube-like morphology could increase the surface area and electromobility of electrode according to Chucky's report. To optimize the population of oxidant vacancy in the TNT, modification of electrodes were conducted by heat treatment, cobalt doping, electrochemical reduction, and a combination of both. We conduct experiments with 4 samples: pristine TNT, cobalt doped TNT, reduced TNT, and reduced cobalt doped TNT. From EDS spectrum of RCO-TNT sample, we confirmed that the cobalt insertion to TNT was successful with the weight percentage of 2.3%. From the darker color of oxide, increased current density of CV, and peak shifting in XRD characterization, we can conclude that the modification gave rise to the oxygen vacancy population compared to pristine TNT.
Optical properties correlates in the ability of photocatalysts to absorb light radiation. In the context of utilizing solar energy, we want the material to have high absorption in visible light, which is represented by the lower band gap. As depicted in DRS spectrum, the combination of cobalt doping and electroreduction modification gives the highest absorption power, indicated by the lowest proportion of reflections. The band gap calculation by Kugelkamu, Fashion, and Tau plot shows a similar trend with the DRS spectrum, with RCO-TNT having the lowest band gap of 1.85 electron volt. A decrease in the band gap indicates a higher presence of oxygen vacancy, which leads to a higher amount of visible light absorption. Then, the electrode's performance in generating photocurrent as photoanode was characterized by MPA test, as can be seen from the graph. All varieties of TNT electrodes could generate photocurrent when exposed to visible light. The order of increase in photocurrent is the same as order of the lowering band gap. The addition of cobalt in TNT improves the transit of electrons, while electrochemical reduction improves the photoactivity by introducing oxygen vacancy and Ti3+ states. Interestingly, the combination of both modifiers gives a drastic 40 times photocurrent improvement compared to pristine TNT, indicating a synergistic effect of cobalt present, Ti3+, and oxygen vacancy of the TNT. The synthesis electrode's performance in nitrate reduction was assessed using LSV with cathodic scanning without light exposure. We focus on the onset potential of 10 mA to gauge performance, where a more positive onset potential indicates better performance. The LSV profiles of TNT and RTNT showed minimal changes in the presence and absence of nitrate ions. In contrast, a positive shift of onset potential was observed for co-TNT and RCO-TNT. Notably, RCO-TNT exhibited the best performance with the onset potential of minus 1.15, signifying the preferential occurrence for nitrate electroreduction to the cobalt and oxygen vacancy synergy. RCO-TNT, the best performing electrode, was utilized using a twin photoanode third cathode, connected to a commercial 3-volt silicon solar cell for additional power input like this. The system begins with light absorption and electron excitation at the photoanode and solar cell, which then will be transferred to the dark cathode. Simultaneously, the water is oxidized to the photoanode. The generated H+ ion is then transferred to the naphthalene membrane to the dark cathode. On the dark cathode, nitrate ion bonds to TNT oxygen vacancies. With electron supply from the solar cell, the H+ from the photoanode, nitrate ions are reduced to ammonia.
After the reaction, the solution was taken. The addition of interphenol reagent revealed the presence of ammonia through the emergence of a blue color with maximum light absorbance at wavelength 640 nanometers. Using a elaborate pure law, the calculated amount of ammonia generated at 4 hours was 0.87 micromole. This corresponds to an ammonia production rate of 0.064 micromole per hour with a solar to chemical conversion efficiency of 0.003% and a ferritic efficiency of 48.24%. In conclusion, we've been successful in constructing the system to generate green ammonia from aqueous nitrate solution through artificial photosynthesis principle. The key was to incorporate a synergistic modifiers of cobalt doping and electroreduction to TNT electrodes which optimize oxygen vacancy. The RCO-TNT has the lowest band gap, highest photocurrent in photoanodic reaction, and the lowest onset potential at dark cathode nitrate reduction. Coupled by a commercial silicon solar cell, the twin 1 cm square RCO-TNT could generate ammonia with a fine production rate, solar to chemical conversion efficiency, and ferritic efficiency.
Although still an ammonia evolutionary, this system provides a promising approach in the future because
It produced green ammonia at room condition,
using a renewable sun energy,
nearly zero carbon dioxide emission,
use nitrate lithium as raw material,
thus reduced global warming significantly and water toxicity.
Thank you!